All right, so after you've practiced your synthetic division on these, hopefully what you noticed is that what I got when I plugged in the values and what I got in the remainder is exactly the same thing. So you'll notice in each of these coming down, and you can check that in your check that in the OneNote with the key that what you got was exactly the same. And it didn't even matter over here. Notice that this one that was in the center here, that I wasn't really dividing by x plus a number. It had that extra coefficient in it. That doesn't even really matter, that still is going to have a remainder of 0. Now, I kind of just did a little side work over here because I just wanted to prove that to myself as I was doing it, that if I were to divide by the polynomial by x plus 3 halves, I get this. And if I divided it by 2x plus 3, that's the same as just dividing both sides of this equation by a half. It also works when the remainder is not 0. This part up here was me just proving it to myself. What if I changed the polynomial and I made the constant -5 instead of -6? So that way I knew it would have a remainder of 1 when you do the division. Dividing by this gives me this over here, right? Same quotient that you would have gotten before, but now you have a remainder of 1 over the x plus 3 halves. If I divide both sides by that extra coefficient of 2, then that divides this by 2, and then it also divides that fraction by 2, and it still has a remainder of 1. So just thought I would mention that because I was verifying that for myself. So kind of the idea of what this is and what we wanted to get out of this is that the remainder using synthetic division, when you're dividing by a linear factor, is exactly the same thing that you would get when you plug the value in. So that kind of gives us two different ways to calculate a value, and that is to simply plug in or do synthetic division. So let's look down at using this. Down here in the remainder theorem in the box is what the technical remainder theorem is. It says dividing a polynomial p of x by any linear factor with a 0 of x equal to a. And I showed that x minus a is typically what we're using it for, but it actually works for any linear factor, provided that if you set it equal to 0, it solves and it has a 0 of x equal to a, that the remainder from the division will be exactly the same as p of a. And this also gives us information about whether or not this value is going to be a 0 of the polynomial. Now notice I said 0 of the linear factor. That's different than me saying a 0 of the polynomial. I'll add that right here. If p of a is equal to 0, then a is an x-intercept or 0 of p of x. Okay, that's what we would know about that. And then what we would also know about that is that x minus a is a factor of p of x. So, and that might be previewing the next theorem that's coming up, which is the factor theorem. In this, the remainder theorem just says that the remainder is p of a. I think I'm getting ahead of myself and heading toward what the factor theorem is, which is the second part. Now let's do a couple of examples just to kind of show you a couple of places where we might see this. So let's look at number 1 here, and I'm going to let you guys do several of these on your own, but I'm going to do the first one for you. It says, for what value of k will the polynomial function, and notice that in this polynomial function, I actually have k right there in the polynomial function. I want to know for what value will it have a remainder of 8 when divided by x plus 2. And so the trick here is that the remainder theorem gives us a shortcut, that the remainder of p of x divided by x plus 2 is going to equal p of negative 2. That's our shortcut. And so you're basically just going to plug that in. So if I plug in negative 2 times negative 8 minus 2 times 4 plus k times negative 2 minus 2. My computer is running a little slow here. It'll get there eventually. And I'm just doing arithmetic at this point while we're waiting for the computer to catch up. So I'd have 16 minus 8 minus 2 minus 2k. And we have 16 minus 8, 8 minus 2, 6 minus 2k. And I want to know, when is that going to be equal to 8? For what value of k? So basically you just have to solve it. Let's subtract the 6 over. That gives me 2. Negative 2k. Divide by negative 2. So k would equal negative 1. And so that, whoops, I did not mean to open that. And so k equal to negative 1 would give me a remainder of 8. So it just turns it into a basic arithmetic problem. All right, I'm going to leave for you to do number 2 because it's very similar to that, and number 3, and go ahead and try number 4. I'll put the key to those in the OneNote notebook, and then you can go and check and see how you're doing on that. So now what I'm going to do is going to go to the factor theorem, which is going to be our next item of business. Now, before you actually work on that, I realized that I probably should show you the alternate method because it gives you 2 ways to do this. Like the first one that I did, I just plugged it in and used the polynomial plug and chug to get it. The alternate method is to actually use the synthetic division to do this. So we could divide by the x plus 2, which means we have a negative 2 as our 0. We can very quickly, because synthetic is pretty fast, you can drop your negative 2, multiply, add to get 2, negative 4, k minus 4. When you add, right, it's okay to have a k in there. And then multiply by that would be negative 2k plus 8. And then combine those together would be negative 2k plus 6. And so the remainder, negative 2k plus 6, we want to know for what value of k would that be equal to 8. Negative 2k equals 2, k equals negative 1. So you can do it in the alternate way as well and get the exact same answer that you would have gotten by plugging and chugging. So it shows you that you have 2 different ways to calculate this. Plug and chug in the polynomial, synthetic division, you'll get the same answer. All right, so now go ahead and do the other 3 remaining ones. I don't really care which method that you use, and we'll come back and talk about the factor theorem. All right, so make sure you check your answers to the previous part in the key. And I'll tell you, I actually think the synthetic division was actually a little faster. I went back and did the problem 2 different ways. And synthetic is such a very, very quick way of doing things that it actually is much faster than actually plugging numbers in. So that gives you kind of 2 ways to look at it. Now, down here, I'll do the first one and I'll leave the second one for you to do. But basically, if I have this function f of x, it's already in factored form. So that's kind of nice here for this. So I know that f of x is equal to 0 at x equal to negative 2, 1, and negative 1. And we see that over here, negative 2, negative 1, and 1 over on the graph as well. So it's fairly straightforward kind of as we're looking at it. But what they wanted us to do is to kind of look at, well, what happens if we were to use synthetic division on each of these factors? So here's the expanded form over here on the side. So what we're going to do, and what they want us to do, kind of do a little box there, is I'm going to take each of these, start with negative 2, and I'm going to divide it synthetically into the polynomial, 1, 2, negative 1, negative 2. And I'm just going to do this fairly quickly. Drop 1, multiply, multiply, drop, and times 2, and I get 0. So clearly you can kind of see that this idea and that what I was talking about above, that the remainder when you divide by something that is a factor is going to be 0. And we can test it for the other 2 as well because, like I said, synthetic division is really such a fast little procedure that we can pretty much, as long as you don't make any arithmetic mistakes as you're doing this, you can very quickly fill it in and get that filled in. So you notice we have 0 there, and then this last one, what are we doing? Negative 1. So 1, 2, negative 1, negative 2, drop, multiply, 1, multiply, negative 2, multiply, 0. So we end up with this idea that we are basically showing that when we have things that are factors of the polynomial that give us the x-intercepts, that the remainder is going to be 0. So kind of relating it back to the remainder theorem, basically what we're saying then is that f of, say here, -2 is going to be equal to 0. X plus 2 is a factor of f of x, okay? And x equal to -2 is an x-intercept, or 0 on the graph of f of x. And you could repeat that. Oops, it would be helpful if I actually showed it to you over here. And you could repeat that for each one of these things. So these are 3 basic facts that we know, kind of taking a look at it. Now, I'm going to let you guys do number 2 here on your own and verify it. I'm going to go ahead and just skip it, and you can just check your answer in the key. What I'm going to do is come down here to, based on the previous examples, what observations do we make about the connection between the zeros of a polynomial function? Okay, so if x equal to a is a 0 of p of x, also known as an x-intercept on the graph, okay, then we know that x minus a is a factor of p of x, that it divides into it evenly, and we know that p of a would have to equal 0, okay? And so those are kind of the things that are the important part of looking at this. So let's go ahead and put the formal factor theorem in the box, and then we'll do a couple of questions. And so basically all the factor theorem says is that if p of x is divided by one of its factors, x minus a, so we put it in that nice little linear format that we have there, that if we divide that by x minus a, and if we do that synthetically, okay, using synthetic division, synthetically, then p of a is going to equal to 0, and p of a is the remainder. So that all kind of ties in what we were talking about up above. All right, let's take a look at some of the problems that are down here that they want us to do. We have a few minutes left. I'm going to do number 1 here real quick, and let's see how we do. I want to know if 2x plus 1 is a factor of that. So I basically am going to find the 0 of the linear factor, which would be x equals -1/2. That is my candidate for the 0 of the polynomial. And there are 2 ways that you can do this. Is it a factor? I could basically do g of -1/2 and calculate that. Or we could take the -1/2 and do synthetic division on 2, 3, -11, -6. And what we want to see is whether or not there is a 0 in that last location. So I'm going to pause and I'm going to let you do that, and then we'll come back and we'll check. All right, so after you're coming back into this, hopefully what you realize is, because I made you do it both ways there, that what you really don't want to do is you don't want to plug and chug. Wasn't it kind of hard with the fractions and stuff to plug and chug? This work over here was much, much easier to do in terms of your arithmetic than it was to actually plug the number in. And so that's the whole point of the factor theorem, remainder theorem, synthetic division, is how nice that is. So I would use synthetic division just like I would do synthetic division on the problems that we had earlier as well. So why don't you guys look at number 2, and you're going to do that one on your own. Let me see, how much time do I have left? I think I'm going to have to end this video here. And I'm going to say that, how much is left here? Yeah, we just have this last page right here. I'm just going to let you guys try that on your own and check your answers with the key, and then work on the worksheet for homework and see if you have any questions on it, because I think that this overall is a fairly easy section. Just know how to do synthetic division and what it tells us. When do you have a 0? It tells us the remainder. Super easy to use. And so we want to use that. So answer the questions and then check with the key.